In cosmology, there is a nightmare scenario. Two independent measurements of the universe are both proven correct, and their results completely contradict each other. For decades, our standard model of the cosmos has relied on a basic assumption. We assumed that at a macro scale, the universe is uniform, meaning it expands at the exact same rate in every direction, everywhere. That assumption is failing. When we look at the cosmic microwave background, the residual radiation from the early universe, instruments like the Planck satellite give us a very precise expansion speed. The early universe dictates a slow expansion rate of about 67 kilometers per second. Yet when we measure the speed of nearby supernovae right here in our local universe, the result is drastically different. The local data tells us the universe is expanding at a much faster rate of 73 kilometers per second. This gap is known as the Hubble tension. A 5 sigma discrepancy suggests that our understanding of physics is incomplete. Applying that faster local expansion rate to the whole cosmos creates an immediate problem. At 73 kilometers per second, the math dictates the universe is only 12.7 billion years old. That age is a physical impossibility. We can observe ancient stars in the Milky Way that have been burning for over 13 billion years. A universe cannot be younger than its own stars. In almost every other branch of physics, physical quantities are highly contextual. The speed of sound, for instance, changes depending on whether it is traveling through air or water. The environment dictates the measurement. This suggests the universe might be fine, but our local environment is skewing the data we are collecting. Solving this crisis requires us to stop assuming the cosmos is identical everywhere and look closely at the blind spots in our specific cosmic neighborhood. That neighborhood is dominated by the KBC Void, a region of space spanning roughly 1 billion light-years. Analysis of the Pantheon Plus beta set reveals that this area is an anomaly. It contains roughly 20% less matter than the cosmic average. We aren't observing from the outside. The Milky Way floats deep inside this giant under-dense bubble, rather than a standard dense region. Lacking matter, this bubble lacks gravitational pull. The surrounding dense cosmic web pulls everything inside outward, away from the center. What we perceived as a typical cosmic environment is actually a massive structural anomaly. Gravity pulls the galaxies inside this bubble toward the denser material at the edges. It is a physical mechanic similar to water flowing toward surrounding mass. Everything in our vicinity is essentially falling toward the edges of the void. This creates a convincing illusion for astronomers on Earth. When we observe nearby galaxies, they appear to be flying away from us at high speeds, as if the expansion of the universe has accelerated. But that speed is a localized effect of gravity. It is not an accurate measurement of how the whole universe is expanding. The Hubble tension suggests that local gravity is masking the expansion rate, hiding the true speed of the wider universe. If the local void theory is correct, the apparent expansion rate should drop back to 67 kilometers per second once we measure objects beyond the bubble's edge. To find the answer, astronomers mapped baryon acoustic oscillations. This precise ruler allows us to look far past our local neighborhood. Beyond it, the expansion curve flattens. The tension vanishes as measurements align perfectly with the global average. This removes the need to invent hypothetical new physics to fix our mathematical models. The standard laws remain intact. It is impossible to understand the macrocosms without first accounting for your exact local cosmic address. Recognizing our position inside this colossal bubble aligns our local observations with the rest of the cosmos, keeping our existing model of the universe intact.